Warning: tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Well, here we are going back to square one. And by that I mean the Nobsound 6P1. This was the first amplifier project that we did on the channel, and I've learned a lot about producing videos and DIY stuff since then, so I wanted to revisit this little amp and do a much better job than we did the first time around, reviewing it, showing the upgrades, and I'm thinking we're going to take this thing a lot further than we did the first time. So, on with the show. So this little amp's got 6 SN7s to drive that are in a Cascode configuration. This is the first time I'd worked on a Cascode, and as you may know, this is what we ended up using with the 300B amp that I've designed. So this was my first introduction to that, but this used a different way of biasing, and I'll show you that when we get into the schematic. It's got a 54UC rectifier tube, which is not a 5U4. This is a Russian indirectly heated rectifier tube that's a pretty decent stout tube. There's nothing wrong with this rectifier tube. We may end up going to solid state rectification, but at this point I'm not real sure. It's got parallel SE design, which means it's a single-ended amp with the tubes are connected in parallel that supposedly doubles the output, but as we'll see, that's kind of a joke, at least the way this amp's set up. These are some 6P1 tubes, hence the name of the amp. There's no US equivalents for this tube. Everybody say hi to Dolly, or bye. These are essentially 6V6s in a small bottle, which is a 12-watt tube. These can handle 250 volts across the tube and 250 volts on the screen. They've got these wired in triode mode, which substantially cuts the power that they put out. It's got no feedback, and as we'll see, it's got some issues. The first one that is a major concern that we're going to address in stage one of working on this amp is the power supply and mainly the power transformer. This has got a 110 volt wound power transformer. Even though it says it's okay for 120 volts, it's not. Tube amplifiers do not have voltage regulation. So the only regulation is the winding ratio in the power transformer. If it's wound for 110 and you're putting in 121, you're basically 10% overvolting everything. And the main issue becomes the heaters and the tubes. When you put 120 volts into this transformer, it's got over 7 volts on the heaters of these 6.3 volt tubes, and it will fry them. And you can tell they're running way hot with a temperature gun. These things are running like super hot. And the other issue is that the transformer runs super hot. I ran it for about 2 hours yesterday with no input signal, just dummy loads on the output, set idle for 2 hours. The top of this transformer was 150 degrees Fahrenheit, which it's going to melt the insulation in the transformer and short out and cause all kinds of issues. There's no way that it can survive at those temperatures. So the first thing we need to do is drop the voltage down to 110 volts going into this thing, which we can do with a bucking transformer, and I'm going to show how to make one of these in a separate video. Or we can use APC has a voltage regulator box that you can set on 110 volts, and it will reduce the voltage down to 110 volts. So I performed the same test after I dropped it down to 110 volts, and the temperature of the transformer came down 30 degrees. So it's still running pretty warm. Might have been 115, but it's still pretty warm. So that concerns me because I know these output tubes are running really soft or lethargic as well. And I'd like to crank them up, but I'm not sure we're going to have the milliamp capacity in the power transformer to do that. The other concern is these output transformers. I've seen these same output transformers, or they look identical to them, on eBay, and they're rated at 5 watts. And Amazon, or this company, rates this amp at 6.8 watts. And so, come on guys, you're not going to get 6.8 watts out of 5 watt output transformers without a ton of distortion. And so we may end up having to replace all the iron to really bring this thing up to what it's supposed to be. But we're going to make some fairly simple modifications on the inside that will bring you at least a couple of watts of clean power, which should suffice for a small system with efficient speakers. I will say that when you drop this thing down to 110 volts, where the tubes are running at the voltages they're supposed to, that the amp loses power too, which is not shocking. So anyway, I think we'll go through the schematic, show you some problematic points. A couple of them are pretty easy to fix. Like I said, one of them is dropping the input voltage. The other one is the first capacitor after the rectifier is at least 5 times bigger than it's supposed to be, almost 10 times bigger. And so we need to reduce the size of that capacitor so that the rectifier tube will live, and then dropping the voltage on the input will make the amp live, and at least then you can use it safely. The next step is going to be changing the way these cast-coded 6S and 7s are wired and operate. And when we go into the schematic, I'll explain that. So anyway, let's go ahead and jump in and look at the schematic and see what the changes we need to make to start improving this little amplifier. Okay, so let's do a quick overview of the schematic. We have it's not actually a 5Z4, it comes with a 5U4C, which actually is a better tube than this is. Got 5 volts going to the heater, and these pull up a lot of amps. And I need to look at what a 5U4C pulls. I'm sure it pulls at least 2 amps, and that may be a way of cooling down the transformer going to a solid state rectifier, but we'll deal with that later. For now, we're just trying to solve the issues that it has as it's built. And this right here is the big problem. This rectifier tube is rated for a max of, it's really low. It's like 4 UF. Without getting into real high level tube stuff, this first capacitor is rated based on how much of its actual current capacity is being used. So when they say 4 UF, they're talking about if you're pulling as much milliamps as this tube can stand. It can never deal with 150 UF. So we're going to replace this with a 22 UF 450 volt capacitor and leave this other 150 UF that's after the choke in place. So that's the main thing we're going to be doing when we go inside this amp, is replacing this first capacitor, and then we're going to be adding a bleeder resistor that goes from this point right here between the choke and this resistor and ground. The other thing, let's go ahead and run through the signal path. Comes the input, here's the volume pot that controls how much of the signal goes to the grid of the lower section of the cascode. Now when you look at a cascode, it's basically turning 2 triodes into a pentode, or a virtual pentode. And that's the easiest way to kind of think about it. So this is our grid down here, This is our cathode resistor and cathode bypass capacitor. This acts like the screen on a pentode would. And when you look at how this is wired, this is pretty strange. And this is acting like a grid leak resistor, and this capacitor in combination with this resistor is setting the screen voltage for this virtual pentode. And it's called a grid leak bias, which is a form of auto bias. And as you'll see later, this is part of the problem with this amplifier. You'll never see another hi-fi amplifier that uses this setup for a cascode. This is used more in guitar amplifiers, and you'll see later in this process, this grid leak bias is what's creating that asymmetrical clipping that we're seeing on the grid of the output tube. So anyway, we have the signal comes, it goes through this coupling cap. This is the grid leak resistor for the output tubes. They're hooked in series, just parallel with each other across the board. It's got one screen resistor to triode strap both the tubes that they share. And then they also share the same cathode resistor and cathode bypass cap. So basically the tubes are just parallel together in hopes that it will double the power. And as we see later, it's not really drawing enough current through both these tubes to warrant there being two tubes in the amplifier, and it's a way of them inflating the output because each one of these tubes is capable of putting out 3.5 watts of power. So without going any deeper into this right now, that's basically the layout of the amplifier, and we'll dive into this deeper later as we dive into working on this amplifier. Okay, so we're going to do a quick scope test on the output of the amplifier, and if you haven't seen my video on oscilloscope testing, I will link it in the description. So this channel up here, which is channel 1, which is this channel, is set on 1 volt per division. So we have 3 volts peak to peak input signal going into the amp, which equals really close to 1 volt RMS. We've got 8 ohm dummy loads hooked up the 8 ohm taps. We got channel 2 hooked across those dummy loads on the output of the amp. And so we're going to turn up our volume knob and look for clipping. Whoa, there it is. And that looks about as high as we can turn it up without hitting clipping. And you'll notice this time that the output is less. On the other video, I got 11 volts peak to peak before we saw clipping. And this time we're getting, looks like 9 volts peak to peak. Well, we're running on 110 volts. And while you could get a little bit of power out of the amp by running it on 120 volts, you will have the tubes and the transformers go nuclear in a pretty short period of time doing that. So this is what the amplifier was designed to run on, was 110 volts. So this is the output that it was made to produce as sold as a 110 volt primary wound amplifier, which is 9 volts peak to peak, which once you do the conversion to RMS volts, which is 3.18 times 3.18 divided by 8, you get right at 1.25 watts that this amp puts out before it goes into clipping. And just like last time, we see it going into really heavy clipping. Let me move this over. It goes into really heavy clipping on the bottom, but the top hasn't started clipping yet. And it was just over half volume when it started clipping on the bottom. And there it starts clipping on the top. and that's a pretty mushed over top of the sine wave. But it's interesting how hard the bottom part clips and how soft the top part clips. This is more what I used to seeing in a tube amp. So we'll dive into it, go internally, see where this clipping is coming from on the next episode. But I wanted to go ahead and show you this before we start diving into the inside of the amp, before we start modifying anything. So again, we pull this over. We're getting 9 volts peak to peak on the output of this amp before clipping. So let's go ahead and end this test and put this thing on the Analog Discovery 2 with the Audio Analyzer Suite and see what kind of frequency versus THD and frequency versus power results we get out of this amplifier as it comes out of the box. Okay, so the first test I went ahead and did off camera was the THD versus frequency, and this isn't as bad as I was thinking it might be. We are only requiring a half a watt of power, but it stays under 10% distortion down here on the low end, and by 100 hertz it's pretty much leveled off. And for transformers this small, that's really not too bad. As you can see though, we're over 2%, and there's almost a percent of difference between the two channels, which could be these China output tubes that we've got in the amp. Again, we will later compare these with the Russian ones and see if we get an improvement in the distortion. The next thing we want to do is let's do a frequency response pull on the amp. And it's a decent sign when it's starting out over here on the left side and not down on the bottom. But we do have quite a bit of roll off here on the bottom end, especially below 40 hertz. From 40 to 100 hertz, it's not horrible, especially for this small of a transformer. So I think with some bookshelf speakers, we should be able to do okay. Hopefully we can improve this a little bit though with some of our tuning. And this little bit of roll off on the top end, it's mostly over 15K, which in my opinion is just really not that noticeable. So the frequency response doesn't look horrible. It's a little bright. You can see it. It's a little higher here on the top end than it is down here. And hopefully we can flatten this out a little bit with some tuning, especially if we decide to go with some shade plate-to-plate feedback. We might be able to shift some of this down to this end of the spectrum. But here's the main one we want to see, is the THD versus power, and we're going to pull it on both channels, and that's not good. Wow, that's some pretty serious distortion. It goes past, if we average, it's going past 1% at 0.08 watts, which honestly, that's better than the 812 did. And once we get up here to 1 watt, we're at average about 3%. And if you remember right, at 1.25 watts is where it started really hard clipping on the scope. But amazingly, we don't really see the distortion turn up or skyrocket till we get to 2.5 watts. But this is some pretty nasty looking distortion, and I bet this isn't good sounding distortion either. So hopefully we can get, I would be happy if we can get, 2 clean watts of power out of this amp by doing some tuning to it, given that these are triode strap pentodes, which is going to cut their power in half and later I'll show you that they're running at about half power. That's probably all we're going to get out of it without doing some pretty major changes to how the output tubes are run. And we need to be careful that we don't melt the power transformer in the process. So there's the rundown on what this thing looks like out of the box, running on 110 volts with the tubes that it came with. And real quickly, I'm going to swap the output tubes from channel to channel and see if the distortion moves with them. Well, just like I thought, when I swapped the output tubes, the distortion moved to the other channel. So I do have a set of the Soviet 6P1P-EV tubes. So I'm going to pop a set of those in the amp and see if that helps any with this distortion we're seeing. Okay, so these are some Wing C, which are the really nice Soviet 6P1P-EBs. I thought they were EVs, but they're EBs. Either way, these are the ruggedized version of these tubes. They do sound a lot better than the China ones that come with the amp. One of the things too, being a parallel single-inlet amp, you really need to have tubes that are maybe not exactly, but fairly closely matched. And as you can see, we have a lot closer channel-to-channel distortion numbers. Not that they're a whole lot better, but it's got this weird little flat spot here. Like right here is where it starts hard clipping on the scope, and for some reason it's showing it as the distortion's flattening out. And I guess this is where we saw the top part of the waveform getting wonky when it starts skyrocketing in the distortion. So anyway, this is about the same kind of distortion levels and power output that we saw out of the A12 amp out of the box, which is a $200 more expensive amplifier. So if you're not going to do anything to the amp out of the box and you're just going to run it, this one has the same output and distortion levels as the $500 A12 does, and it's a $300 amplifier. But still got quite a bit of distortion, and I think with a little bit of tuning, we can make some major improvements to how this little amp sounds. So let's wrap up this video. So as you can see, out of the box, without opening this thing up, but operating it on the correct 110 volts that it's designed for, this thing doesn't even come close to the advertised specs. Like we saw on the scope, we're getting 1.3 watts, and distortion, asymmetrical clipping, it's got some issues. And again, like I showed you, we were going over the schematic, the extra large size capacitor is also going to be problematic, and it's going to wipe out the rectifier tube and stress it out to the point where they're not going to last long. So we can go inside it, replace that one capacitor, add a bleeder resistor for safety, close it back up, operate it on 110 volts, and at least then we know we're not going to be frying tubes. And if you have some really efficient speakers and you only need maybe a watt of power, that it may work good enough like it is. But there's another fairly simple mod that we'll do in the next video that really takes this little amp to the next level. And I think you'll have a lot of fun doing that. It's only about $5 worth of parts, if even that. So we'll get into that in the next video. We'll open the amp up. We'll start changing components. I'll show you where everything is and how to do this yourself to make this a usable little tube amplifier so you can experience what tube audio sounds like. Anyway, I hope you're enjoying this video. Hope you like my channel. If you do, please subscribe. Please like the video. And we'll see you soon for more Nobsound 6P1 fun. Have a great day.